I think it's time we start with our webinar. So welcome to the CEEGS project webinar called Challenges and Risks of CO2 Storage. My name is Marko Komac, and I represent one of the partners in the project, and that is European Federation of Geologists. And I will be your host for this webinar. Of course, the main words and place goes to the presenters. So as the first presenter, I'm really happy to present our coordinator of the project, of the CEEGS project, Ricardo Chacartegui. Ricardo is a professor, and I can assure you, by knowing him personally, he's probably one of the nicest professors I've ever met. And he's a professor at the Energy Engineering Department in University of Seville. He obtained his PhD in 2005, and since 2006, when he started to work in research domain, he has more than 100 papers registered in Scopus and more than 800 publications in international congresses since that time. His main research fields are related to energy storage, novel energy systems, and LCE technologies. He has participated in more than 60 projects in collaboration with industry, and he has participated and being co-author of 9 patents, not 7. So please, Ricardo, you can start with your presentation when you're ready. Thank you.
Okay, thank you very much. Thank you. So it's a pleasure. Thank you for I'm probably very exaggerated with in the introductions. There are nicer professors than me. I'm sure that some of my students will consider that. So I'm the project coordinator of this consortium, the CEEGS, and very exciting project. And I'm going just to present the main concept, and the things that we want to make within the period of the project in order to put you in context. We will have a number of workshops related to different aspects, and this is a very relevant about the CO2 storage approaches and issues. We have a wonderful number of speakers. So Sole, Cornelia. So, do you hear me now better? Do you hear me? Javier said that it was very bad the sound. My apologies. So I share my screen. I will try to I've been using it a few minutes ago that the sound was good, but my apologies. Sorry. Okay, now you see my full screen. This is the complete number of our project, CEEGS, Novel CO2-based electrothermal energy and geological storage system. And here you have our web page. You will see that we are putting all the information, news, open access deliverables uh, in the web page, so you can see how we are evolving. You will see that it's quite nice, the advances that we are having. What is behind this project? So the idea came, let's take this one. The idea came for integrating a Carnot battery uh, moved by renewable energy to and based on transcritical carbon dioxide to store this renewable energy storage using the underground to store mechanical energy with the CO2 underground. So we have a project in which we are trying to identify the viability of the concept for storing renewable energy using geological formations and with additional benefits related to, depending on the location, of geothermal, partial CO2 sequestration in the terrain, and to analyze if it is worth to advance in the pathway about the project. So our efforts are focused on the interface between the surface component and the subsurface components, where there is an knowledge gap because it's the first application with these characteristics. It's important to understand that compared with a permanent sequestration of CO2 underground, in this case, we are considering first an operation where CO2 is provided, creating the plume, filling the system, let's say 1 year, 2 years. It has to be defined depending on the site. And after that, we have, once achieved the requested pressure to maintain the stability of the terrain, so it operates in closed loop. And it operates fluctuating around the maximum and minimum pressures adequate for geological stability of the system. So it starts operating in open loop to fill and then operates in closed loop. And also it requires partial supply of CO2 because a part of the CO2 will be sequestered in the terrain. So at the end of the project, we expect to have to achieve the technology readiness level of 4. How we make this energy storage? We make it in both ways, mechanical, with the compressed CO2, and thermal. We have thermal storage tanks that operate around 150 Celsius degrees, the hot temperature tanks, and we have around 0 Celsius degrees in the cold temperature tanks. It means that we can use, for instance, water and ice slurry in order to operate. So also using affordable, sustainable thermal energy storage means for the tanks. Using CO2 as a working fluid has some benefits regarding the characteristics of operation, regarding temperature and pressure, the potential capacity of lateral migration of the CO2 and then partial sequestration in the terrain, and that also can be of interest for some constraints at geological level, and also the potential thermal benefits using thermosiphon effects and enhanced geothermal heat extraction. It's also because we have a hot temperature tanks, high temperature tanks and cold temperature tanks, we have the potential of integrating not only the power capacity, electricity, renewable electricity storing, electricity delivery in the discharging phase, but also we can integrate in the hot tanks, hot water tanks, in the cold ice slurry tanks, we can integrate district heating and cooling systems for application to industries or services. What we want with the project? So what we want is to provide scientific proof of the technological feasibility of the transcritical CO2 cycle integrated with the geological storage in complete different circumstances to the traditional ones used for CCS. Who we are? So we are 10 partners from different locations, parts of Europe, and also we have 20 associated entities representing that comprises Geologists Federation of 20 different countries. So it's completely extended to Europe, and it can have a huge impact if successful. And we have at the same time the return, a very valuable return from different approaches and different locations. Regarding what we are doing, a novel concept integrating thermoelectric energy storage based on reversible transcritical CO2 cycles oriented to renewable energy, and that allows energy storage in form of electricity, thermal, and CO2 storage for mechanical work. Why we do it? Or why we consider that it is worth to advance in this? Because it's an scalable system with the potential for high performance, high capacity energy storage. It can be used for electricity storage and production, heating and cooling, and also providing partial CO2 sequestration. Because of the scalability, the potential, the wide diversity of potential locations, the concept minimizes cost and surface impact. So, compared with the application only on the surface, the energy storage capacity is increased by a few orders of magnitude. So making really interesting about it. And also, it has the potential of delivering energy in different approaches depending on the specific cases for district heating and cooling, for industries, or electricity. Uh, just how it works, the concept. We have heat pumps that with renewable electricity increases the pressure and the temperature. Uh, Heat is exchanged with the hot tap temperature and is injected in the geological system. It's in a closed loop, so we have that it's closed, coming back and returning to delivering, extracting heat, sorry, of the low temperature tank. This is in the charging mode, this one that I'm following with the pointer. In the discharge mode, we have that the fluid is delivered from the well A and takes heat from the heat previously stored in the charging mode and expands the turbine and condenses in the low temperatures. Here, the hot temperature, the high temperature tank and the low temperature tanks are the system that makes the coupling between the charge and discharge cycles. The difference of closing here with the geological storage, instead of going directly, is that we have a huge amount of energy and also the additional benefits that they said before of of using transcritical CO2 in geological formation because of the increase of energy storage capacity and the cost effective development. Where is the knowledge and technological gap here? What happens if we are making this strategy integrating both? How we are addressing it? So, three main challenges. What about the integration of surface and subsurface components to the system? Conceptual design, we are in an early stage technology, so conceptual design for novel components adapted to requirements. And finally, the third challenge we are addressing is the analysis with the results obtained in the analysis different answering the two previous challenges to make the techno-economic analysis of the feasibility and impacts that the technology, if finally developed at commercial scale, would have. We are now in the middle of the project, and this is the structure we are having. Analysis of geological environments, analysis of the transcritical CO2 systems and component designs, the integration of renewables and the optimization operation modes, validation of the model with a pilot plant, the surface component, and based on data of wells, and the social, economic, and sustainability. And that's a short overview of the project. Very fast, I know that a lot of questions not answered, but we are running successfully. And thank you. That's all from my side. Here you have, please visit our website and also our LinkedIn profile. You will see a lot of information. So, thank you very much.